so you're welcome to go and find videos from past days. I will try to continue to post the models that we build the next 2 days there as well, so you can get sort of that model in case you didn't get certain things in it. Again, these are the URLs here. Any of the TAs can help you with that. Okay, so we had talked earlier about multiple types of modeling, and system dynamics, agent-based modeling, discrete event modeling. It turns out that I've argued that these days, the issues in using these techniques, it's not so much a matter of picking which one will be your tool going forward for your next model and for your career. It's a matter of weaving them together. And this is a reflection of the fact that these methodologies are highly complementary. They're often best used to address different needs, answer different types of questions. And I think it's fair to say that no one system science methodology offers a replacement for the others. You can twist yourself into knots to do things you can do in one with the other, but you'll find that each has a natural realm of application that that recommends it as a very appropriate tool for that and very efficient tool for that realm. And there's real synergies and benefits that can be secured by combining these techniques. There's many motivations for performing hybrid modeling. This is what we talked about. Each of these techniques has a comparative advantage, so it's very nice to represent portions of our model in one as opposed to another. Often we want to speak to stakeholders who prefer to encounter with one as opposed to another. Maybe it's clinicians who are used to thinking about encounters with particular patients and find stocks of patients that count the number of patients unfamiliar. It may be cases where we're dealing with individuals who are very keen on involvement with the model and find a discrete event model comfortable in a way they don't in agent-based models. So, dealing with stakeholders is the key thing. But often there's also a need to evolve the model in a flexible fashion as learning takes place, and we want to shift the boundary between different techniques. So we're going to just glimpse very quickly here, because I really want to get us hands-on, 5 different ways of combining these sorts of techniques to give you some feel for them. Now, I have a longer lecture, maybe I'll say a long-winded lecture of me on this topic, posted about a month ago. I also have a whole page which gives hybrid model after hybrid model after hybrid model that illustrate different techniques. But I just want to highlight for you what's possible to give you a sense of what can be accomplished and why these sort of hybrid models are not minor things, why they're really valuable. And I've accentuated sort of 5 different examples. The first of them has to do with the one we're going to be building in another half hour or so. So here we have a population, and I've shown them crudely as a population of dots. Those are to represent people, okay? And these people are in a population. They may be in networks with each other, representing their family connections. Perhaps it's connections having to do with collegial relationships. Maybe it's connections having to do with certain risk factors, such as sexual contacts or needle sharing. These individuals' status evolves over time, but these individuals, when they become ill, when they need to secure a service, they will present for care in a facility, and that facility will have a map drawn according to a discrete event model characterizing the progression of people within this facility. Now, why would you use a discrete event model? Why not just keep that all as an agent-based model, this area up here? What does discrete event model make really easy to do? To describe the dependence of that flow on what? On workflows. That's a key part. and on, begins with a big R, ends with an E. It's true that the spatial layout can be captured really well, the range over which the agents move and so on. Absolutely, but I have an additional word in mind. I won't play hangman with you, but it has an S in the middle of it. Resources. Resource. It's going to depend on how it depends on resource, how that processing. And part of that is where things are placed, the ranges over which the agents move, how far they have to go for certain quantities, etc. It can capture all that endogenously in a beautiful way, in a way that's very crisp, transparent, and doesn't require a lot of work to describe it. That's really attractive. So we could ask very easily questions, what if we increase the number of senior clinicians here, or the number of attendings versus the number of residents, or suppose we were to add an additional room, how much would that reduce the waiting time, how much would it allow people to flow through the system with quicker service completion time. Okay, and then these individuals, when they're done with their service presentation, they flow back to they sort of go home in the population. This is a very common model, and we'll see that. We'll build one of these. Okay, it's going to be a chance to explore both these sorts of modeling. This is another representation. We have people in their homes, and we have particular service delivery places which have logic, and those people get sick and present for care. Okay. Another thing would be a situation where we have a model that represents the broader population in a very aggregate way. We saw this yesterday. No, we did see it. It was there. The broader population, and at some point, once they become a population of greatest interest, of greatest risk, of where we need to represent them in more detail, they're butted off as agents. Here, they're just numbers. We count the number of people who are at risk rather than individuating them, but they turn into agents with all the benefits of agents. Capacity to put into networks, to have a GIS location, the ability to have their history tracked, all those sort of things. We capture them in this population here. So, and by the way, we could have them then flow back to the aggregate population after that if at some point, we've dealt with their needs and they're at lower risk again. So here we can get great economies by not needing, both in terms of how quickly we can build the model and in terms of how fast it runs, by characterizing the broader population in an aggregate way. And then this agent population, we can have the great specificity you want to simulate targeted interventions, to simulate interventions that might depend on a person's history, their episodes of care that they've encountered or what have you, through this more detailed model. This is a very practical and flexible technique, and ultimately we can shift the boundary, right? We could shift it back here and capture this at-risk population at individual level if we deem it helpful to do so. This is a second form of hybrid modeling. System dynamics on the left, agent-based modeling, and potentially discrete event modeling, both of them individual level on the right-hand side there. Any questions about that one? Okay, this is going to be sort of a whirlwind tour of these different types. Let's talk about another one. We may build this at some point. So this is another agent-based system dynamics hybrid, but here the arrangement is different. It's not a lateral arrangement where those who are aggregate go on to become agents directly. Instead, what happens here is within an agent, we have their evolution described by system dynamics quantities, as well as potentially other types of dynamics that aren't described by system dynamics. So system dynamics is used to capture the continuous variation in a given person's fatigue level. We saw that in Dylan's model, for example, the other day with the paradox of primary care, the adaptation of that model that from Kurt Stange, where he added fatigue on the part of carers. Those carers had a stock and flow within that carer representing how much fatigue they had. And it turns out that there's a lot of theoretically grounded models that are characterized using system dynamics for everything from body weight change and body composition to factors having to do with immunological dynamics to factors having to do with fatigue and the impacts of work pressure, et cetera. So there's a lot of theory that's captured with differential equations, with stocks and flows. And we can capture it quite crisply and nicely within an agent by using system dynamics for that agent. Alternatively, this agent might be a piece of furniture in a long-term care facility, and this represents the stock represents the buildup of pathogen on that dining room table within the long-term care facility in a way that might expose other human agents to pathogen. So all of these cases are cases where this sort of hybrid technique might be possible. Here we have, for example, exactly that method being used to build up the pathogen levels at workplaces and within homes here. So it's a pathogen reservoir. And in other cases, we've used that here in our province to map out risk areas to be able to characterize a model which could characterize burden of West Nile virus in different areas, the number of mosquitoes in different areas of the province as characterized by system dynamics, where each patch is a region of land within our province. Taking advantage, of course, as we can, of the fact that our province is, as Lauren Calvert once said, the easiest to draw and the hardest to spell. Second to last type, the penultimate type, is agents driving aggregate system dynamics. So here we have agents at a low level. We have system dynamics at a high level. This gets a little bit to Joachim's question. Dynamics feedbacks from a high level to a low level. This is one popular way you could have agents. Maybe these agents represent tobacco companies or fast food chains or what have you. And we might have a population of people, for example, up here divided into categories, and we're simulating how these agents end up affecting the flow of the health of the broader population. Or maybe this is environmental dynamics, and these are people operating within this environment. And we want to have, in many cases, some feedback from that high level to this agent level at the low level. This is a sort of common multi-level model. And we can readily build it using the tools that we're going to be getting you onto in less than 10 minutes now. So here we have these kind of different levels, a low level with agents, a high level with stocks and flows, system dynamics, and we can capture the interactions between them in a very favorable fashion, with much of the stocks and flows operating according to values of stocks, but some drawing on the values of the agents. Finally, we can have this is actually what I was just referring to. Environmental dynamics at a high level, say the number of infected mosquitoes and so on, can affect an agent population of people. It would be computationally burdensome if we had to create an agent for every mosquito in Saskatchewan. Would you agree? Particularly during late July and those lazy days of early August up north, where the mosquitoes come thick and heavy in the evening. Having to allocate an agent for every one of them would be computationally burdensome and unnecessarily time-consuming. So we might deal with a very aggregate model of mosquitoes, and then agents are predated upon by mosquitoes. So here we have high-level dynamics affecting the agents within the model. And so we have those pathogen reservoirs infecting particular people here shown in in a somewhat disconcerting pose. And we actually had, yeah, okay. So I think we'll leave this we'll leave it at that level for this conversation. I could go on and elaborate on this in much greater detail, but I have that video online. I'd like to get you on the ground doing push-ups. What do you think? Okay. So I'd like you to first fire up your AnyLogics. Okay? Okay. Now, I think your machines are going to be